Here in this section, we're going to look at something called implicit differentiation. So we're going to look at kind of a different notation for taking a derivative. So we've seen this a little bit before, but it looks like this: d over dx. This means taking the derivative of something with respect to x. So the change in the function divided by the change in the independent variable. So we want to differentiate a function, find the derivative of a function with respect to the change in the independent variable. We usually think about y as representing the function or the dependent variable. That's another name for that, so a dependent variable. This usually represents the output, in other words, and x representing that independent variable. So what we've been saying is change in y over the change in x is usually how we think about this, which is kind of another way of saying slope. Change in y is like the rise, and change in x is like the run. And we know that the tangent line, we're talking about the slope of the tangent line, is what we usually refer to as the derivative. So we're going to take this function here. So you have y equals f of x equals 2x squared minus 16x plus 5. And really what we're doing is we're taking the derivative with respect to x. So I want to find the derivative of this function with respect to x. And how we usually think about that is this right here, dy dx. And that's like our slope of our function, so the slope of the tangent line. So what we're doing is we're finding the derivative of basically kind of both sides of this equation. So d dx, taking the derivative with respect to x. And if we do that, of course we know we're using the power rule here. 4x minus 16, and this represents that derivative, which we also refer to using the notation f prime of x. This represents the slope, or the change in y over the change in x, the slope of that tangent line. Well, so that's really nice if you have y by itself on one side and then the independent variable on the other side. But what if we can't easily separate y to be on one side and x to be on the other? What if we can't easily solve for y? So in this example here, we had y solved on one side. This is basically, it was explicitly, kind of explicitly solved for y. So we knew exactly what the function was and what it looked like in terms of x. Implicit differentiation allows us to take the derivative of an equation even if the equation doesn't have y by itself on one side. Alright, so this is what we're going to be talking about in this section. How do we find the derivative if y is just part of the equation and can't be solved for on one side using that function notation? So we're going to be using this notation here, d dx. Now, we usually refer to x because usually we refer to x as that independent variable, but the independent variable could be other things. It could be that we're taking the derivative with respect to time, so that would be d dt. Or taking the derivative with respect to something else, or taking the derivative with respect to price, or there could be anything that we could take the derivative of. And remember that this right here would represent whatever independent variable that you're working with. And the top value represents whatever you are taking the derivative of, whatever function that is. Whatever the dependent variable is for that equation. So one thing that we want to note is we know that the derivative of x is 1. We've been taking the derivative with respect to x all along. So if you think about it like this, we're taking the derivative of x with respect to x, dx dx. Of course, anything divided by itself is 1. We usually don't write that. We usually just take the derivative with respect to x. If I take the derivative of y with respect to x, if I don't know what y is, then I just leave it just like this. If y is not explicitly defined, I don't know what y really is equivalent to in terms of its function, but I do know that I want to take the derivative of it. We can just write it kind of in words. This is the derivative of y with respect to x. So I don't know what the actual function is, so I don't know what the derivative is, and this is kind of in a way, kind of a placeholder to say, if I knew what y was, then I would take the derivative of it. But we don't know what y is, so we're just going to say dy dx. That's the derivative of y with respect to x. And so the key here for this whole entire section is to remember that y is the same thing as f of x. In other words, y is a function of x, where y is the dependent variable. I know we've said this a few times, but it's really important. And x represents here the independent variable. Okay. Everything here goes back to the idea of the chain rule. Okay, all goes back to the idea of the chain rule. So let's just remind ourselves really quickly of the chain rule before we go on. So remember that when we were talking about the chain rule, okay, let's say that we have our function y equals, let's say, let's do 3x plus 2, and I raise that to the power of 4. Okay. So since I know what y is, it's by itself on one side, then I could say, well, the derivative of y, so let's just use this notation here, the derivative of y would be equal to 4, bring that exponent to the front, and then the inside function raised to the power of 3, and then we multiply by the derivative of the inside, which would also be 3. Okay, so that would be our chain rule. We just want to remember what that is. Now, when we come down here, we don't know exactly what y represents. In a way, we're kind of saying we don't know what the inside function is, but we still want to take the derivative of a function. So let's look at this here. I want to take the derivative of y squared with respect to x. Okay, this all boils down to basically the chain rule. Treating y as a function. Now y, we don't know what it is exactly. It's not explicitly defined. It could be a big parentheses with a bunch of terms in it raised to a power like we saw here. We don't know what this inside function is. So that's the problem. Well, just assuming that it's a bunch of terms, something that's more complicated, let's assume that y is just a bunch of terms raised to a power of 2. So y squared. Well, in order for us to take the derivative of that, we're going to employ the chain rule. Okay, we have a function raised to a power. Okay, that's kind of how we want to think about it. We want to think about it as just some function raised to a power. So how do I take the derivative of that? Well, chain rule, we said. So you bring the power out to the front. We write the function as is, the inside function as is, and then we multiply by the derivative of the inside function. Okay, so this is just a chain rule. But we just don't know what f of x is, but we can use the notation to imply what we would have done if we would have known what y was, or that function was. So another way of writing this would be 2, and then the function itself is also the same thing as just writing y, and the derivative of y with respect to x. So don't know what that derivative is, but we can also use this notation to describe the derivative of y with respect to x. So those two kind of notations say if we had known what y was, we would have done the entire chain rule, but since we don't know what y is, then we have to just kind of notate what we would have done if we did know what y was. Okay, so basically implicit differentiation is all about the chain rule. Alright, so let's look at this one here. Here we have 2x squared plus y squared equals 16. We want to take the derivative, let's do this, we want to take the derivative of both sides of this equation with respect to x. So we're going to do d dx. I'm going to do this to both sides of our equation. We want to think about any term that just has an x in it, we're taking the derivative just like we always have done. So on this side, of course, taking the derivative of both of these terms is basically the same thing as taking the derivative of each term separately. So we'll think about it like that. Taking the derivative with respect to x of each of these terms separately. Alright. Okay, well, what's the derivative of 2x squared with respect to x? Well, we've been doing that all along. What's the derivative of that? Well, that's just the power rule. That's 4x. Now, any term that has a y in it, this y, keep in mind, it's really important that y represents a function of x. So x represents the independent variable, y is the dependent variable. So in order to take the derivative here, we're going to have to use the chain rule. So we're going to bring the power to the front. I'm going to write the inside function, which is y, as is, and then I'm going to multiply that by the derivative of the inside function. Well, the inside function is y. What's the derivative of y? Well, we don't know what y is, so we don't know what the derivative is, but we'll just say, okay, we'll multiply that by the derivative of y with respect to x. Okay, so we're just kind of putting that implied derivative there using that notation. Equals, okay, well, the derivative of a constant. Okay, there's no x there. There's no change. This is like a horizontal line. Once again, the same thing we've always done. Taking the derivative of a constant, we get 0. Okay, so we're taking the derivative, but anytime we're dealing with a function or a dependent variable, we are going to include one of these factors, dy dx, as the derivative of the inside function. Now the last thing I want to do is solve for dy dx. So I want to get that term, or that factor, all alone. So in order to do that, for step 2 here, I'm going to bring every term over that does not have dy dx. So that's going to give me 2y dy dx. All three of those things, of course, multiply together there in that term. I'm going to bring over the 4x to the other side, so that becomes a negative 4x on the right-hand side. Now, since it's 2 times y times dy dx, I'm going to divide both sides by 2y. So I want to cancel out the 2 and the y, and I'm left with now dy dx. That's negative 4x divided by 2y. So this is the formula for how I would calculate the derivative, the change in y with respect to x. Now, the only thing here is that I would have to know both the x and y value of the point for which I want to know the slope. All right. So in this case, we have 3 terms that have variables in them. And x represents our dependent or independent variable, so we're going to take the derivative of that the same way that we always have. And then y is our dependent variable, so we're going to have to treat those as functions of x. So we're going to take the derivative with respect to x of both sides. So take the derivative with respect to x of x cubed plus y squared plus y minus 4. Take the derivative of the other side as well with respect to x. Now, of course, we said taking the derivative of 4 separate terms, we can do them separately. So let's do that. Well, taking the derivative of x cubed with respect to x, well, we can just take the derivative using the power rule the same way we always have, because there's no y in that term. So that's just the independent variable, so we're going to do it the same way we always have. Now, this one we're going to treat as a function. Remember that y is the same thing as just some function f of x. So we're going to have to use the chain rule anytime that we see that dependent variable y. So we're going to say that would be plus, we'll bring the 3 to the front, going to write down our inside function, and I'm going to raise it to the power of 2, and then we always multiply by the derivative of the inside function. Well, we don't know what y is, so we'll just have to say, well, if I did know what it was, I would take the derivative of it. We're going to write this dy dx as a placeholder to represent the derivative of that inside function y. Okay, the next term also has that dependent variable. Now this time it's just y to the power of 1. So, take the derivative of y, well that's just the derivative of y, dy dx. The derivative of negative 4 with respect to x, well, that's a constant, so that's just 0. And on the other side, we also have the derivative of x with respect to this constant, also 0. So now you have something a little bit more interesting. We want to solve to get dy dx by itself on one side. So really important, the first thing that you do is you look for the term that does not have dy dx, and you bring that term to the other side. Okay, so we have two terms left on the left-hand side that do have dy dx. On the other side now we have negative 3x squared. Okay, well, I have two dy dx's, so I have dy dx in both of these terms. So we're going to factor out dy dx from both terms. So that leaves us with 3y squared from the first term, and anytime we take out a complete factor from one of the terms, then we have to leave a 1 as a placeholder. Okay, so remember, if I multiply that back in, I get back what I started with. Well, the last thing that I want to do now is divide by anything that's not dy dx. So I'm going to divide both sides by 3y squared plus 1. So those cancel out, and I'm left with my final result. The derivative of y, derivative of the function with respect to x, would be negative 3x squared divided by 3y squared plus 1. Now this one's a little bit more interesting. Here we notice that we have x squared minus 2x times y equals 6. So here you have to be a little bit more careful. Anytime we have two variables multiplied together, we have to think about using that product rule that we've talked about in the past. So we're going to take the derivative with respect to x of both sides. Okay. So we'll take the derivative of each term separately. The first term only has an independent variable, so we're going to take the derivative of that the same way we always have. That's going to be 2x. Now the second term is where things get more interesting. First of all, we have two variables multiplied together, which definitely implies that product rule. One of them is independent, the other one is a dependent variable representing that function. So I'm going to go ahead and just pull out my negative 2, and we're going to focus on taking the derivative of just this part right here, x times y. So I'm going to focus on just that part. So we'll pull the constant to the front and just focus on taking the derivative of x times y. Okay, well, we'll treat x as the first, we'll treat y as the second. So it's the first times the derivative of the second. Okay, so once again, y is the second. Well, what's the derivative of y? Well, we don't know what y is, but so we just imply this the derivative of y with respect to x. Okay. Plus the second as is times the derivative of the first. Well, the first is just x. What's the derivative of that? Well, that's just 1. So we have to employ the product rule here anytime that we see two variables or variables multiplied together. So two little mini functions, in other words. Of course, on the other side, the derivative of 6 with respect to x, well, that's a constant, so we end up getting 0, just like always. So let's simplify a little bit here. That's 2x. Let's multiply back in that negative 2. So that's negative 2x dy dx plus, or let's say negative 2 there too, because we're going to distribute the negative along with the 2. So negative 2 times y times 1, well, that's just negative 2y. The last thing I want to do is solve for dy dx. So very important, the first thing you always want to do is the same process every single time. Bring over to the other side any term that does not have a factor of dy dx. Okay, of course, when we bring it over, the signs change. So that becomes negative 2x, and then plus 2y. And then the last thing you want to do is divide by anything that's being multiplied in that dy dx term. So anything that's not dy dx. So we're going to divide both sides by negative 2x. So our derivative of y with respect to x becomes negative 2x plus 2y divided by negative 2x. Now you want to be careful here. If you want to reduce that, you can, but you want to be careful of something. When you cancel things out, you have to factor first before you cancel. So I could factor out a 2. In fact, I could factor out a negative 2 if I want. That leaves me inside with x minus y. So the only thing that's going to cancel here is going to be the negative 2 factor that's common in the top and the bottom. So if you wanted to reduce this, I'll write my final answer right up here. This would be x minus y divided by x. So those negative 2's can cancel. So this should be fine. This really is okay too. But if you want to reduce your fraction, factor first, cancel out common factors.